All right, thank you, Luis, for the introduction, and thank you very much for the invitation. Good morning, everyone. And before I start, I have a question, Eben. What did you have for breakfast? How can you boost your energy like this early in the morning? It's amazing. I'm afraid to have set the standards quite high, but I'll try to deliver anyway, okay? Well, my lectures are going to be about mobile laser scanning. And just before I start, for anyone who doesn't know me, I'm a forest engineer from Brazil. I had a master's degree in forest management through an Erasmus Mundus program. I stayed in Göttingen in Germany and SLU in Sweden, in where I worked with terrestrial laser scanning, and as a side product of my dissertation, I had the 3LSR package, which I completely refactored this year, and it's available open source, and it's a highly efficient package for processing forest data from TLS and now MLS point clouds. So maybe some of you have heard of it and are using my tools. I'm very glad about it, and any discussion we can have about it could be done this afternoon, maybe. Well, my lecture is my talk is gonna be mainly about mobile laser scanning, but as I know, not everybody here was properly introduced to the terrestrial laser scanning universe. I'm gonna make an overview of forest inventory very shortly, then address how we evolved in terms of terrestrial laser scanning processing on the last 20 years, until we got to the moment where we are with very performant mobile laser systems, and some discussions at the end of the talk. Well, forest inventory has been done since the 14th century. The first registers of forest inventory date back to Europe, about 600 years ago. So it's something that has been performed for quite a long time. And we have improved a lot in several aspects throughout those years. For example, statistical sampling methods, better technologies for managing, manipulating data, storing data, georeferencing, and a lot of technology involved more in the planning aspect of it. But regarding actually measuring the trees, we have developed some quite handy devices to help us on field, but it doesn't really reduce the intensity of the field work. It's very labor intensive, you still need people to do it, and the devices can be quite technological, but they are still based on simple trigonometric principles, and not really reducing efficiency in terms of field work. Well, those field surveys are quite risky because sometimes you have to put down the trees, you have bees on your way, you have animals, you have all sorts of problems and risks you have to face. Those are quite labor intensive, time consuming, expensive, and they're very prone to errors. So humans, they make mistakes, and it's quite easy for you to guess a height of the tree in a wrong way, or mismatch a diameter or something like this. So humans are prone to errors, and depending on the forest type, it's even harder to get good data out of field plots like we have nowadays. And in an era in which you can digitize pretty much everything, we can put the machines to do the hard work for us. It's going to be done eventually, even in forestry, even if you want it or not. The machines are going to take over, especially the labor-intensive, repetitive work like this. And while remote sensing came to aid forestry in a more intense manner on the last 30 years, I would say. So we have input a lot of data from satellites, aircrafts, and more recently drones, like images, photographs, and point clouds, in order to aid us to deliver better maps out of the properties, in which you have a very high accuracy description of your whole area, just very robust and with good precision statistical models for predicting biomass, volume, and pretty much any quantitative variable related to the forest, which is very much enhanced in terms of precision and error when you combine it with remote sensing data. But nevertheless, those area-based approaches of using point clouds or images, whatever, they still require field work. You cannot really measure anything from an image or from a point cloud up to this point, I mean aerial data. You still need something to correlate with. So if you measure heights across a forest profile or in a whole area, or you measure intensity, RGB, hyperspectral, whatever, it's not something that tells you directly an information about the tree. You're not measuring the volume directly. You need to correlate it with some other variables which are very, they fit very well with the interest variables you have in the forest, and then you can model those using regression and some machine learning and have a good prediction of biomass, volume, ecological features. If you really want to measure something, you got to go down below the canopy. So terrestrial laser scanning comes as an approach that makes it possible to really reconstruct objects in 3D. Before you had a coarse description of a forest profile, for example, but with terrestrial laser scanning, you are increasing your point density by a huge amount. You're going to have from tens to hundreds of points per square meter to several thousand points per square meter, and then you can really see. If you look a point cloud like this, you can really recognize the object in there, and if you zoom in, you can even see branches and leaves, and depending on the resolution of your sensor, you can really segment everything. So the first applications of TLS in terms of forestry, they sprout on the early 2000s, and they were mainly focused on reproducing what we do in regular forest inventories, like measuring dBH, height, and counting trees. It was based on those very robust sensors from Faro, Rigo, or Leica, which are quite expensive, but they deliver very good data. And the first experiments were very successful. We could really see that you can measure and extract diameters, heights, and see the trees very well, even in automatic manners from those point clouds. But soon after, on the last 10 to 12 years, some way more complex algorithms have been applied and developed, and individual trees sometimes. So algorithms that extract very complex features from the point clouds, like flatness saliency and grouping statistics for calculating metrics point-wise or voxel-wise or in point neighborhoods, adjusting optimized methods for circle estimation, cylinder estimation, applying graph analysis for getting the branch structure of the trees, topological analysis to get the actual shape of the boles and how the trees grow. So there is a huge range of algorithms out there to process and analyze different types of forests, trees, and scenarios in general. Those algorithms have been applied in terms of forest inventory to a few very high-level applications, such as separation of wood and leaf biomass, estimating, making the stem segmentation and point classification of woody material, crown architecture, and the most advanced application of it are the quantitative structural models, in which you can fully reconstruct, or at least you try to fully reconstruct a tree, applying cylinder models stacked together that are able to reproduce all the structure and the volumes with high fidelity. Well, we actually got so many algorithms and methods published and validation that we were able to get to a point in which a benchmark could be done. This paper was published last year, and it compiles several methods, most of them are automated, that tested and validated, that were tested and validated in different plot scenarios, from difficult, which are small stems, very densified, close together, up to areas with sparse trees with larger diameters. And the methods validated came from extracting ground points to build DTMs up to stem segmentation, passing through heights and diameters and taper curve. So the main outcomes of this huge effort to validate and benchmark the available methods out there gave us a few conclusions. On the best case scenarios, I mean, the best case scenario of data was already studied in this paper, because they only analyzed point clouds taken with very high resolution static sensors, like it was a Faro sensor, if I'm not mistaken. It's a few millimeters of accuracy, point-wise. And then they validated all those algorithms on those point clouds. And on the best case scenarios for the algorithms application, I mean, the algorithms which performed best, they achieved errors, percentual errors in terms of 10% for stem curve and dBH for the best plots. And for volume and biomass, it was in the range of 20 to 45% of error for estimation. So those are quite high errors for volume, but regarding heights and dBH, the estimates are quite good. There were some expected outcomes of this paper, since you scan using TLS, which is positioned in several static spots across a plot or across a landscape. You cannot really fully cover a forest, especially if it's very dense. So you cannot really see all the trees sometimes, and you cannot reach the top canopy. You cannot get the very last point on every tree to measure the true height. And then you have some bias downwards in terms of how many trees you can count automatically and how high, how tall those trees are. And well, just wrapping up the TLS part of the presentation, we can split the TLS in forestry mainly in two realms, which is hardware, more focused on field surveys, and software, more focused on data analysis. So on the hardware side, we have great data quality. We had already 10 years ago great data quality, but the setups were quite complex in terms of field logistics, because you have to install several reflective targets on field, and depending on the forest you are, you have to be able to see all the targets from every scanning position, so the logistics have to be very well planned. It takes a very long time to scan everything, because you have to be moving the tripod with the scanner everywhere, putting the targets on places you can see all the time. And the scanners by themselves are quite expensive and time-consuming to apply, so it's not really operational in terms of market, in terms of the forest industry. You cannot really measure several plots every day in 100,000 hectares forest of eucalyptus or anything commercial. And regarding software, we already had a variety of automated methods for extracting the main forest variables, dBH, height, and even some trials to get the volumes and full biomass of the whole woody material from the trees. But as I told you before, some large errors regarding volume happened, and some bias downwards in terms of height and tree count. So, and they were not actually performant in all forest scenarios. If you have a sparse plantation or a sparse tree patch, and if the trees are large and they are not really close together, you can have very good estimates, very good tree detection. But if you have a very dense point cloud with trees very young and very close together, small stems and so on, it becomes harder and harder to get good performance out of the automated methods. And then, of course, you have to have very skilled personnel to work on those data for you. It's not really available there as a software. And well, this makes us think about how to make things easier in terms of logistics of applying this hardware outdoors. Because as I told you, we used to install several reflective targets on field, and they have to be positioned in several ways across a plot, so you can have the best coverage in terms of 3D space you can have. So some trials attempted to do this co-registration of multiple scans using simplified targets, or even getting rid of those at all. Some things have been able to be done, but then we realized, well, if you really want to see everything in the forest, you got to move inside of it. So the first trials to apply mobile laser scanning came by just putting a terrestrial static laser scanning on something that moves, but you also have to combine it with very robust hardware for localization and for attitude. You really need to know every second you are taking a point cloud, where it is positioned in the landscape, and how it's oriented. And it's not really easy to do this inside a very dense outdoorish environment like a tropical forest or even a planted forest. If you are looking for millimeter or centimeter precision and accuracy, that's not really the way to go. And then we had to combine with technologies from other scenarios, and thank God there is technologies from computer vision and autonomous navigation that developed a magical algorithm called simultaneous localization and mapping that came from processing photogrammetry data, but it was later applied to 3D data using the LOAM algorithms, which is LiDAR, odometry, and mapping. And those algorithms were originally developed to work on easier scenarios with more geometrical features across the landscape, such as buildings and something flat, and there you can really see easily how they split into different surfaces. But then they got more robust and more robust, several groups working on it, and you could even extract very good data sets in terms of point clouds from outdoor environments as well. The first attempts, they were quite robust already, but they lacked in terms of localized accuracy. So the first devices that were applied into forestry in a mobile manner, they could be called personal laser scanning, handheld laser scanning, wearable laser scanning, chicken laser scanning, whatever you may call it, and moves in the forest. You can give it a name, but essentially it all moves in the forest, so it's mobile laser scanning. And the first attempts to apply SLAM inside the forest environment, they were quite good globally, but the SLAM algorithms, they suffer from a few pains, let's say. If you scan for a long time on very long paths, your point clouds might drift, so you have a very good localization in the beginning of your walk, but by the end of it, you have drifted to somewhere else. And globally, it looks really consistent, but when you zoom into the objects you're trying to measure or segment, you see there are some localized inconsistencies. Like some trees maybe don't match, some diameters that should be on the same spot, they are not exactly there, they drifted a few centimeters apart. So it's not really good for applying this on high precision forest inventory. And when you think about applying the low-cost portable sensors like the Velodynes, in which you have already by default from the manufacturer a higher error in terms of point precision, about 2-3 centimeters, then those drifting errors become even more apparent, as you can see by those cylinders here that have multiple walls, one inside the other, and it really doesn't make sense.